Okay, this is going to be the part 2 video for chapter 789, unit 2 for AP statistics, and we'll pick up where we left off here. Let me share my entire screen because we're definitely going to need the calculator today. All right. So we said that normally we would collect data by having the class go out and write down their heights and then the number of steps they took to traverse a distance. We mentioned that in the last unit. And this is actually some data that we collected from one class. So we're going to enter that data in a calculator. And like most of the time, we're going to use the lists under stats. So you could click stat and then edit and then enter the data. And this is one continuous table. So this is on the bottom of this. So I went ahead and entered the heights of all the heights here in list 1, because we believe that should be our explanatory variable x. And then in list 2, instead of the frequencies, I'm just copying things. So if there's duplicates, I just type the duplicates right in here. But now the second list is contain a different variable. So in this case, it's steps. So it's important, these can be in any order, but once we've established an order in list 1, the points have to be matched straight across the rows between list 1 and list 2. So this x goes with this y and so on. So you can pause the video here, go ahead and enter that entire data set in to the calculator, which is what I've already done. Okay, now that the data is entered, we're going to go through the steps to get the calculator to display the scatter plot for us. So we'll say second mode to quit out of that, and then go second y equals, go into a statistics plot menu, turn it on, and then for the type, we're going to select this first icon, the one that looks like some rows of dots here. That's the scatter plot icon. We have to tell it where the x's are. That's in list 1. So if that doesn't say that, you can say second 1 and then enter. And then for the y list, second 2 for L2. And you can, I like to use the default little box here for each data point. Then we quit back to the command line, and then we press zoom and then 9 to display the plot. And then we have the scatter plot, right? So it's just like we suspected. As people are taller, they tend to take fewer steps to cross that, right? And we would say that there is a negative, fairly strong linear association between steps and height. Okay, so these are the steps for setting up a scatter plot. Okay, so let's talk about some terminology and get into the detailed calculations. So there's two words that are used in connection with these x and y pieces of data. One is the word association and one is the word correlation. So in this class, there's a specific meaning and difference between them. The word association is a general term that just means there appears to be some kind of relationship between the variables. So when we're describing the association, we use general terms like linear, fairly strong, negative, right? The word correlation is specific. It's a precise term that is a measure. It actually is a measure of the strength and the direction of the linear relationship. So it's a numerical number. In fact, correlation is synonymous with the correlation coefficient, okay? And the letter that's used for that is R, okay? So R is the correlation coefficient. I believe it comes from R meaning relationship, but it doesn't matter. If you go looking on the internet for things about correlation coefficient, there's many subtle differences. This is the Pearson's correlation coefficient, which is the standard one, the one that you've been exposed to in previous math classes. Okay, so there's a formula for computing it. And basically what it is you take the z-score of an individual data value in the x direction and the z-score in the y direction, right, which would be at that data value minus the mean, like the x value of a data value minus the mean of the x's, divided by the standard deviation of the x's. That's the z-score in the x direction. And then this is the z-score in the y direction. The y for that point minus the mean of the y's over the standard deviation. And then you multiply those together, and then it's the average. So we add them all, all those products up for the product of the z-scores for all the points, and then average them. We actually divide by n-1 for that subtle reason. Send me an email if you're interested in that. But basically, it's the average of the product of the z-scores. Okay, so the important thing, though, is that it gives a number, and that number is always between -1 and 1. A correlation coefficient R of 0 means there's no association between the variables. So just to kind of see what it looks like, well, let's first talk about why it is the way it is. So let's say we had a data set here. okay? And what I'm seeing here is that there's a couple blue points here that basically the X and Y is kind of right on the average, right? So if you took a data set, let me actually do this. If we had this data set X and Y, and we had some sort of data here, okay? And then we said, well, where is the mean of the X's? So there's some value here, which is the mean of the X's. And then if you look at all these Y's, there's some value, which is the mean of the Y's, right? And there's actually a point right here, which is the mean X, the mean Y. There's a name for that point. It's called the centroid, okay? But if you were to take the z-score, like let's say, for example, I took this point right here, right? And I wanted to find its z-score in the x direction, right? That means you would take the data value x minus the mean of the x's over the standard deviation of the x's. So this point here, we would say, well, what is its difference? It's x value minus the mean x value. And then we would divide by the standard deviation of these x values to get how many standard deviations we are to the right. So maybe that would turn out to be 1.5 standard deviations, right? And then if we did the same thing for the y's, maybe we would find that this point happens to be 2 standard deviations away from the mean in the y direction. And so that's why this point has a z-score of about 1 in the x direction and about 2 in the y direction, right? So if you did that for every one of those points and figured out, you know, what is the standard deviation in the x and y direction, right? Here would be the centroid right in the middle here, which is 0 away in both directions. So what I see is that this trend is mainly positive, right? So what will I get for my correlation coefficient? Well, if you looked at all these points that are kind of along the trend, right, all of these points have a zx that's positive and a zy that's positive. So when we multiply them, I get positive numbers. All these ones down here have a zx that's negative. In other words, the z-score in the x direction is negative, and the z-score in the y direction is negative. So when I multiply those, I also get a positive. So all these green points are places where the zx times zy are positive, and all those things are going to add a bunch of positive numbers into my sum of the z-scores. I'm taking the average, so it's going to add a bunch of positives in there, right? If I have a data point, by contrast, that's in this quadrant, this one has zx, which is in the negative direction, but it has a positive z in the y direction. And so when I multiply those, I'm going to get a negative. So these points would add some negatives in. And also here, where we have positive z in the x direction, but a z-score that's negative in the y direction would also be negative when we multiply those. So I've got a few points that are adding in negatives, but a whole bunch of points that are adding in positives. So that means that this is going to overall be some positive number, right? And that's why positive associations have positive correlation coefficients, okay? So if this was confusing, don't worry too much about it. Knowing the details is not super critical, although it'll help us later. The main thing is we want to know, how do we find the number for our data set, and how do we interpret the number, okay? So let's show how to do this in a calculator. We've got our data entered, right? And we can run statistics on it, but there's something we have to do first. And that is, we have to turn on something which should be programmed on by default, but is not in the TI calculator. So if you have a TI-84, you have to, every time you clear your memory, you got to go back and do this. Go to Mode, and then scroll down to Stat Diagnostic, and then go over here and turn that on. Okay, so that you just have to do that once after you clear memory, and then it stays on. For TI-83s, it's more complicated. You have to find a function to run in the catalog of functions. So see where it says catalog down here under the 0? If you hit the number key, the second key in the 0, you can scroll down to the D's by hitting the key that's above the D somewhere in here. Let's see, where's the D? Right there. And then you just scroll down to find this right here, diagnostic on. You have to enter that on the command line and hit enter it to run it. That turns on the stats diagnostics. I'm not sure why they didn't do that by default. They should have. Okay, but to get this correlation coefficient, we have to do something called running linear regression. Now, you may have done this in previous math classes, maybe not, but I'm going to show you the whole thing. We're going to do it slightly differently than the way they did it. And we'll talk about how to interpret the whole output later. Right now, I'm just after getting the correlation coefficient. So what we're going to do is we're going to go to Stat, okay? With our data in list 1, list 2, we're going to scroll over to calculations, the same place where we had our one variable stats, but we're going to scroll down to item number 8, linear regression in the form a plus bx. What that's going to do is try to fit a line to this data that fits as well as possible. We'll talk more about exactly what that is in a second. But right now I'm just going to need this to get my correlation coefficient. So we'll select that. You have to tell it which list to use for X list. That's list 1. List 2 for Y's. Frequency is 0. Just leave all the rest of this blank, and then just go ahead and hit calculate. Okay. So what it'll do is it's going to give us some information about the equation of that line that fits the data, which we'll talk about later. But right down here on the bottom, it tells me the R. R is negative 0.873. Okay, so I'm going to write down the result. R is negative 0.873. And while we're at it, this R squared is just that R except squared, so it's always positive. So for our step height data, we ended up with a correlation coefficient of negative 0.873. All right, so how do we interpret that number? Well, we said that the correlation coefficient would always be a number between -1 and 1. Okay, so if you had an R value of exactly -1, that would mean that wherever the line was drawn, these points were literally right on top of the line. Every single point was literally on top, so that almost never happens. And the reason it's negative is because this is a negative association. If the same thing were true but with a positive slope, where the points were right on the line, then the R would be +1. Okay? If you have no discernible line at all, in other words, if you try to draw a line, you couldn't even figure out the direction of the slope, so you just draw it like that, that would be when R is exactly 0. But most correlation coefficients are between 0 and 1 or between 0 and -1. So the fact that we had a negative association, right, means that we're somewhere in here, right? And basically, the closer the points get to being all on the line, the closer this -1 number gets to exactly -1. So like if I drew a line through this data like that, kind of through the middle, these points are reasonably close. Maybe you would call this -0.5, halfway between. And this one is a positive. These points are +0.5. So R goes between -1 and 1, almost never gets the endpoints, right? Or even this, but so R -0.8, the fact that RR was -0.87 means that we're somewhere between these two kind of things. And sure enough, when we looked at the scatter plot, it's a little tighter grouping than this, but not as tight as this. Okay, so whenever we draw a trend line like I did here, we're going to do that frequently just to estimate things. It's always a line. We never use curves, okay? And then the idea is wherever I draw this line, about half the point should be above that line and half below, right? And that means that the average distance, and if you were to take these distances, the average on the top and the bottom, they will always add to 0. The average of the pluses and minus differences would always be 0. So imagine if you kind of drew a line in that way. All right, so these are the possible values, right? You can kind of attach these with different words, although there's no standard way to do this. Right, I would say anything where an R value is less than 0.2, so somewhere between -0.2 and 2.2, we would say there's no association, right? A correlation coefficient that's between 0.2 and 0.5, or -0.2 and -0.5, I say we would call those weak associations, typically. Between 0.5 and 0.8, moderately strong, and something has to be above 0.8, so 0.8 to 1, or between -0.8 to -1 to be called a strong association, although it kind of depends on context. So what this R is a measure of how close the points are to the line, okay? And we'll talk about why it's got this weird name later, okay? All right, so that's how correlation coefficient works. There's some things that have to be true for us to do a correlation coefficient. One thing is both the variables have to be numerical. You can't have something like pet and then, you know, I don't know, age or something like that. Yeah, this is numerical, but you can't compute correlations for categories, right? So you have to have both variables quantitative. Also, correlation coefficient is very sensitive to outliers. So sometimes we'll talk about the effect of outliers in a later part of this, but sometimes you try removing points or putting them back in and seeing what result that has, right? And we'll talk about how you can predict what's going to happen. R, the correlation coefficient, has no units, right? Because since it's the product of the z-scores, and z-scores have no units, it has no units. Some people incorrectly report it as a percentage, but it actually has no units. And then it turns out that R is unaffected by changes in the center or the scale of either variable. So if I decided to report my height instead of in inches in meters, that would have no effect on R, right? Because since we're using z-scores in the computation of it, the units are already removed. So it doesn't matter if you change the x and y. It doesn't matter if you change the units that are used. The R is unaffected by those things, okay? Okay, so at this point, we usually do a required practice number 3. So I'll ask you to pause the video and do that. And then I'm going to go ahead and go over it next. Okay, so in part 3, we're back to, or question number 3, we're back to that car weight fuel efficiency thing. And it says, which of these values for correlation coefficient do we think estimates this the best? So I would draw my line kind of through the middle of the points, some of them above, some of them below, right? And then I would kind of, I'm going to disregard this at first, right? And just say, just look at the data in general, right? These points are quite close to the line, not exactly on the line. The line is negative, so I know R is going to be negative. And then really my only choices are these two. And since these are pretty close, I think I would go with negative 0.9. That's my estimate. Although this point is far away and will weaken the correlation a little bit, not enough to balance out all these points close to the line. So that would be that right there. Okay, so hopefully you got that right. All right, let me switch back to the notes here, and we'll see how far we're going to go before we stop for this part. All right, so a couple of quick kind of quirky things about the correlation coefficient. One of them is that the correlation coefficient really only measures the strength of the linear association. And it actually becomes invalid when the slope of that line is either close to 0 or close to infinity, okay? It's just an affectation of this weird thing that we're taking the product of two z-scores. Okay, so let me give you some examples. Let's say you had data that looked like this, okay, where the slope of the line would basically be 0, right? There's no discernible trend here, right? If that's true, what's going to happen is the correlation coefficient will be really close to 0. In fact, I actually computed it to be 0.2. The reason for that is that for every point that's above this line that has a positive z in the y direction, there seems to be kind of a balancing point that has a negative. So these, no matter what the distances are in the z, they're sort of having some positive ones balancing negatives, and they sort of cancel to 0. So you end up with correlation coefficients close to 0 when you have a slope of 0, right? So it's hard to tell things about how widely spread this is. So it basically doesn't work very well then, right? Also, if you had, let's say that the average of the x's was here, and the average of the y's were here, so this point right here is the mean x, mean y point, the centroid. You know, anytime we have a data value that's close in either direction to the centroid, that z-score is approximately 0. So even though these points have some z's in the y direction, right? The z's in the z's in the x direction. The z's in the y direction are all approximately 0 because the distance from the mean is 0. So when these points are lined up and this line is practically horizontal, right, we will also get a correlation coefficient very near 0, okay? So you really can't tell whether the data is spread widely or closely if you have a slope of the line going through there that's close to 0. It just kind of breaks down, right? And it also breaks down in this direction. If the slope of the LSRL were nearly vertical, that's because all these zx's are approximately 0. The number of standard deviation in the x direction is 0. So it wouldn't matter if the points were like that or if the points were all spread out, but the line through them was this way. You couldn't really tell anything, right? And then the biggest thing is to note this. If you happen to have a really strong association like this, but it's not linear, if you try to draw a line through that line would just be a horizontal line. Some points above, some points below. And so this also will have a correlation of 0. So even though this is a strong association, the fact that it's a nonlinear association means that the R will still be approximately 0. So the correlation coefficient kind of fails in these cases. You don't get a valid number for nonlinear data. You don't get a valid number where the line through the data is horizontal or vertical, okay? So just keep that in mind. All right, the next thing we're going to talk about is this line. How do you find the line? How do you find the equation of the line? Okay, so first of all, the equation is called a least squares regression line. Okay, and the least squares part, we abbreviate that LSRL. So I'm going to use that phrase a lot, LSRL. Sometimes people call it a linear model or a line of best fit or a trend line, but this is the official term for our class, least squares regression line or LSRL. So if you drew the line in such a way that some of the points were above and some of them were below, then there would be a difference between each actual value and the prediction that you would get for that X on the line, okay? Every one of these has a little difference here, these differences, like here's one difference here. And that difference is called a residual, sometimes given the symbol E, because it means that the model for the line is not perfectly predicting the data value at that X value variable, okay? So this length here is called a residual, and it kind of represents a slight error in the model. So we have the Y, the actual Y, right, for a data point. But then if we were to come up with an equation of this line, which we're going to talk about how to do in a second, we could plug in an X value and get a predicted Y. So we have to have a different symbol to indicate the predicted Y versus an actual Y. So the way we indicate the predicted Y is we put this little hat on top of the Y. It's called Y hat. This is also sometimes referred to as a caret, spelled that way. So Y hat is the predicted X, or sorry, the predicted Y for that X on the line. And just Y without the hat is the actual Y for an actual data value. And so the residual is defined, let me write it this way. The residual is defined as the actual Y minus the predicted Y. Okay, so it's the actual Y minus the predicted Y. That's very important. And that means that all of the data points that are under the line all have negative residuals. And all the points that are above the line have positive residuals, right? And there'll be generally a balancing of the positive and negative residuals. That's how the line is formed. In fact, the reason why this is called a least squares regression line is they take all these residuals, they square them all so they're all positive, and then they just adjust the line until we have minimized the square. So it's the line that has the least amount of values in the square of the residuals. Okay? Least squares. Regression, there's a different meaning for that, which is more subtle, and I won't really try to explain that, but the least squares thing, okay? In fact, you can kind of look at this. If you were to have, let's say some data here. So you've got a data point, data point, data point, data point, data point, data point. Here's the centroid here. And you were to fit a line to that, then you could think of all these residuals, right, as errors. And then you would want to adjust the line to try to minimize the squares. In fact, let me see if this is still active. Maybe I can show you this. There's a little demonstration that I usually show in class. See if this is still active. Yeah. Okay, yeah, so here we go. So here are some data values here, right? And I've got this this thing where I can adjust this line. So if I take the residual, like this blue one right here, and I square it, that's actually going to give me like this square. It's like an area. And this square represents the square of this residual. So the bigger these areas are, the bigger the square of the residuals are. And so what happens is we just try to like basically change the y-intercept and the slope of the LSRL until we've minimized that completely, right? It turns out actually that it's this line right here. This is the line that has overall the least amount of error. So it turned out that it was better to let this one be really out of whack because these other ones were so close that compensated for that. So the calculator has a way to basically do that, to kind of try out different y-intercepts and slopes and then keep track of this and keep adjusting until that is the smallest error possible. Okay, we're never going to try to do it by hand. We will always do it in a calculator. So I want to show you how that is done. Okay, so This is how you do it in a calculator. So you have your data in there, which we have our step height data in here, okay? And we go ahead and run that linear regression like we did before. Now, this is where when I say stat calculate, I'm going to select, there's two linear regressions. There's number 4, which says ax plus b, but we're going to run this number 8 linear regression that says a plus bx. Okay, and the reason for that is in this course, a is our standard symbol for the y-intercept, and b is the standard symbol for the slope. So I'll run that, okay, on list 1, list 2. And then that's the same thing we did to get the correlation coefficient, right? But right above that, you see how it says that y equals a plus bx, and a is 53.8 and b is negative 0.57. What they're doing is telling us coefficients to plug in here. So they're saying you can make your regression line this way by writing it as y. It should really be y hat because it's the predicted y, is the y-intercept of 53.8471, right, minus the slope of negative 0.5728 times x, right? And typically, that's the way I would write an LSRL. So I would write it that way, but then I would write separately what the x and y are. So in this case, the y, or the x is the height, and I would provide maybe the units, and then the y is the number of steps, okay? Right, so when we're ever asked to write out an LSRL, we're going to put the data in a calculator. This is one way to do it. And then we're going to run this linear regression, number 8, and then we're going to write out y hat equals, this is the a plus bx, and fill in the a and the b. If the b is negative, this becomes a minus. And then we'll write what the variables are. Sometimes some problems might have us actually fill in the names of the variables right in there. Like if the y variable steps, this could be steps hat, the predicted steps is 53.8471 minus the slope times the height, and write in the values. Okay, so you might see it either way. All right, so that's how we get the data from a calculator, okay? So here's the idea, right? This a right here, this a value, is the y-intercept of the line. In other words, if the x value was 0, this would be the y value, okay? And then the b, this is the slope of the line, right? In other words, for every 1 unit in the x, the y goes down by this amount, okay? You don't have the textbook right now, so you don't have to worry about this, but for some reason, well, I know why, but our textbook uses b0 for the y-intercept and b1 for the slope. But throughout our course, we're going to use a for the y-intercept and b for the slope. So this is the y-intercept of the line. Okay, and then AP Stats, this AP Statistics exam very frequently asks us to write a sentence to explain the value, okay, in context. So the idea behind the slope is for every 1 increase in the x, the y either goes up or down a certain amount, right? And so in this context, our slope is negative 0.5728. So the way we would write that up, and you need to know this for the test, would be for every 1 added inch in height that a person is, the number of steps decreases, because this is negative, by 0.728 steps on average. And you always have to put that phrase on average in there. The other way you can do it, instead of writing on average, is you can say for every 1 added inch in step, the predicted number of steps. So you can also insert predicted here to cover that. But the idea is we have to put a little bit of kind of weasel wording in there, because we're not saying that if a person is an inch taller that their number of steps drops exactly this much. We're saying that on average for the whole data set, or the predicted value is that, right? But basically this is just an explanation of slope, right? It's kind of like you would say in algebra, right? For every 1 unit over in x, y goes down 0.57. That's what we're saying, except that the x is an inch in height and the y is a decrease in number of steps. Okay, and then if we ever have to explain the y-intercept, a lot of times it doesn't have a meaning, like in this case, right? But sometimes it does. So that would be if you had a person who was 0 inches tall, then the model predicts that they would take 53.84 steps on average to cover that distance. Right, so if we're asked to explain it, we just go ahead and explain it, right? But in this case, it's kind of nonsense, and frequently it will be, right? Because a lot of times we have situations where the x variable being 0 is impossible, like height. You can't have a person with 0 height. Okay, so very important to be able to explain either the y-intercept or the slope in context. All right. Okay, so why would we have this model? Well, the main reason we want this linear model, this LSRL, is so we can use it to predict the y for a given x, right? And so if we have a data set that covered, let's say, x values from here to here, right? Then anywhere in here, it's okay to use the LSRL to predict things, right? That's called interpolation when we do that. When we're saying, okay, I didn't have a data value at, say, this x value, but I could plug that x into my equation and get a predicted y for that, right? However, we should be cautious about using it anywhere outside of where the data was, because that means we're assuming that this linear trend is continuing, right? So when we do that, if we try to use that for a data value that's outside of the range of the data, that's called extrapolation. And the official word is that we should avoid doing this entirely in stats. Right now, in the real world, what we often do is we do go ahead and use this for predictions a little bit outside of the data, but we try not to go too far out of there because we're assuming that this linear trend is continuing, and that might not be true, right? We might have a data set that right now the data looks like this, and we're like, yes, we got this nice model, awesome. And then we might find out, and so we use it to predict. We say, oh, well, what's the value for this x? And we predict that it's right there, right? But what we don't know is it might be that for some reason, like this year, the data changes and now it's looking like this, and so our prediction is wrong. So it's dangerous to go outside of where the data was that was used to produce the model. And that's called extrapolation. So that word we have to definitely know. All right. So let's say we're going to use it. So what does the LSRL predict the number of steps would be if a person was 59 inches tall? Well, that's easy to do. All we need to do is, now that we've written out the LSRL, we can just plug in the value for x that we want, right? So I would just fill in 59 inches here and then just calculate that. So if I just go, okay, 53 point, what is it, 847, we used a little bit of rounding here, minus 0.5728, and then we just multiply that by 59, that's going to give me a predicted y, right? So my predicted y would be 20.05. So I'm thinking approximately 20 steps is what the model predicts, right? So even if I didn't have a person who happened to be at 59 inches, I can get the predicted value for a person who was 59 inches tall, right? And then what would we predict for a person 82 inches? Well, we would do the same calculation, right? We would just fill in 89 for the height, and this time we would get, so in a prediction, if somebody was 82 inches tall for x, right, our LSRL predicts that they would take 2.86 steps. Now, should I trust that? I don't know. They're going to cross that. That distance was actually quite far, and I can't imagine somebody doing that in 3 steps. So this is outside of the range, right? We only had data up here till about 74. So somebody 82 inches tall is definitely in the region where we would call this extrapolation. We should either avoid it altogether or maybe at least use caution. Caution. Trusting the results. All right. Okay, at this point, we would stop typically and ask you to do problems 4, 5, 6, and 7 in the packet. So I'm going to ask you to do that. And then let me take a quick look at those and see if I want to cover them as part of the video. Yeah, I think I will. So normally we would have you work in groups or turn to someone next to you and do these problems. So do that now, and then we'll work through the next thing. Okay, so I'm assuming you're unpausing the video now, and we're going to go ahead and go through this. So this says, the table and scatter plot below show the relationship between student enrollment in thousands and the number of burglary and theft property crimes for 8 colleges and universities. Basically, it's showing this trend that the higher the number of students are, the higher the number of burglaries and theft there are in the region of the college. So it says, use the calculator to find the equation of the least squares regression line. And so what we would do there is enter this data. Now, I want to keep my steps and height data in there, so I'm going to switch to using list 3 and list 4, just because I don't want to overwrite my old data. So I'm going to put the enrollment numbers in my list 3. So 16, 2, 9, 10, 14, 26, 21, 19. And then I'll use list 4 for my Ys, my property crimes. 201, 642, 141, 138, 601, 230, 294. Okay. And then I will run least squares regression, so stat calculation number 8, but I'm going to use list 3 for my x's and list 4 for my y's because that's where I put that. Okay. And then I'm going to go ahead and hit calculate. Let me write down what I've got here. So I've got that the y hat would be negative 112.58. I'm going to abbreviate a little bit, with a slope of positive 21.8x. And then whenever we do that, we always want to identify the variables. So x here is student enrollment in thousands. And then y is going to be the number of property crimes. Okay, so we always have to identify what variables are being predicted here. So that's what we would write for the least squares regression line. Okay, for part 4, it says interpret the slope of that in context. Okay, so the slope, let me just write it out. The slope is 21.8, okay, and the units of the slope would be, like all units, change in y over change in x. So it's property crimes, let me just write it, it's crimes per 1,000 students, right? So basically what that's saying is, for every additional 1,000 students, property crimes go up by 21.8 crimes on average. So that's in fact what I would write. Let me write that since this is an explanation using the text. I would say for every one additional 1,000 students enrolled, property crimes are predicted to increase by 21.8 crimes. Or if you didn't want to insert that word predicted, you could say crimes increase by 28.1 crimes on average. In fact, let me just write that. Here's another. These are the 2 ways that are allowed on the AP test. For every additional 1,000 students enrolled, property crimes increase by 21.8 crimes on average. Okay, so you either have to use the word predicted, you have to use the word predicted somewhere, or you have to insert the phrase on average, just to indicate that it's not being guaranteed for any particular college, but this is the trend. Okay, that's how we would do number 5. And which ones were we going to? Up to 7. So let's do 6 and 7. Okay, how many crimes would you predict on campus with an enrollment of 14,000 students? So let me write out the LSRL again. We have y hat equals negative 112.58 plus 21.8x, okay? Where x was the students, number of students. That's the number of students in thousands, and y was the number of crimes. Okay, so 14,000 means that we should be putting in the x value 14. So I'm just going to show that being done. Computations on tests, you have to show what you're doing, so you have to write that, and then just go ahead and do it and calculate. Right, negative 1112.58 plus 21.8 times 14. So it looks like the number of crimes predicted would be, let's see, 192.6 crimes. Okay. I think in this case, you could, any computation, generally you can leave it not rounded, but it would also be correct to say approximately crimes are predicted. That would be okay. Okay. So to use the LSRL, we plug in an x and get the y. Okay. And then the last one, find the residual for the campus with 14,000. So we just said that 193 was predicted, right? That's my predicted my predicted y hat. Okay, so that means that there's going to be an actual y, because sure enough, we had a campus that actually had 14,000 students, and the actual number of crimes was 138. Remember, we said the residual is equal to the predicted y. Sorry, it's the actual y minus the predicted y hat. So in this case, the actual y is 138. The prediction was 193, right? And so that would be 138 minus 193 is negative 55 crimes. Okay, interpret the value in the context. So whenever they say interpret, that means they want a sentence. We could say for 14,000 students, the residual of negative 55 crimes means that the actual number of crimes was 55 crimes lower than the number of crimes predicted by the model. Something like that, right? For 14,000 students, the residual of negative 55 means that the actual number of crimes was 55 crimes lower than the number that was predicted by the model. All right. All right, so that, I think, is it for that. Yeah, for now. Let's go back to the notes and see. I think that might be the end of what we're going to cover. Yeah, that's the end of part 2. So we'll pick this up in a third video.